Physical World, Chapter 1, Section 12, Digging Deeper, Describing Earthquakes. Earthquake Intensity. You analyzed earthquake data using a map. To do this, you ranked an earthquake's intensity in various locations. You then used descriptions given about the effects of the quake. You also looked for patterns in earthquake intensities in various locations in the eastern United States. The effects of an earthquake on Earth's surface are an indication of its intensity. As you learned from the United States Geological Survey's Did You Feel It website, intensity scales are based on certain key responses to the shaking of an earthquake. Examples include people awakening, damage to brick and stone structures, and movement of furniture. The intensity scale used in the United States is called the Modified Mercalli Scale. There is no quantitative basis for this scale. It does not use mathematics as part of its description. It is simply a ranking based on observed effects. This is similar to what you did in the Investigate. Earthquake intensity is a measure of the effects at a certain location. Intensity value is important to the average person. It has more meaning than a magnitude value. The greatest intensity is often observed near the epicenter. However, there are exceptions to this rule. Sometimes areas with the maximum intensity are not nearest to the epicenter. In the Mexico City earthquake in 1985, the epicenter was hundreds of kilometers away. However, areas within the city experienced much higher intensities. Modified Mercalli Scale of Earthquake Intensity. Description of effects. Okay, so on the scale, if the earthquake has a value of 1, it's not felt except rarely by a few. If the value is 2, the earthquake is felt by a few, especially on upper floors of buildings. Delicately suspended objects may swing, such as something you have like those lights that just hang from the ceiling. All right, a value number 3 is felt indoors by some. There's a vibration felt that's similar to a passing truck. It's not always recognized as an earthquake. A value 4 is felt indoors by many, outdoors by few. It awakens some sleeping people. Dishes, windows, and doors rattle, walls creak, standing cars rock, hanging objects swing. Okay, a number 5, Roman numeral 5 on the scale of earthquake intensity is felt indoors by mostly everyone and outdoors by many. It awakens most sleeping people. Some dishes break, windows and plaster walls crack. Small unstable objects get overturned, such as cups and staplers and things. Hanging objects indoors swing considerably. Pictures are knocked out of plumb, meaning that they tilt a little bit. Some liquid might be spilled from full containers, so this is a pretty big intensity earthquake. All right, value 6 is felt by everyone. There's general excitement and some fear, slight damage to poorly built structures, considerable amount of glassware and windows break. There's some furniture overturned and some heavy furniture is moved. Pictures and books fall from walls and shelves. Fallen plaster and damaged chimneys. Small bells ring. Okay, an earthquake with the intensity of Roman numeral 7 on the scale. Everyone's frightened. Some have difficulty standing. There's negligible damage to well-designed, well-built structures. Slight damage to moderate and well-built ordinary structures, and considerable damage in poorly built or designed structures. Weak chimneys are broken, large church bells ring, trees and bushes are shaken, water in lakes and ponds is disturbed. Some stream banks collapse. An 8 on the scale, on the earthquake intensity scale, is there is general fear, approaching panic, slight damage to structures designed to withstand earthquakes, considerable damage to ordinary structures, great damage in poorly built or designed structures, heavy furniture such as couches and tables is overturned, chimneys and monuments topple, sand and mud are ejected from the ground, changes in flow of wells and springs. Intensity number 9, general panic, considerable damage to structures designed to withstand earthquakes. Well-designed buildings are shifted off their foundations. There's great damage and partial collapse of substantial buildings. The ground is noticeably cracked. Some underground pipes crack. Getting more intense. Number 10, severe damage to well-built wooden structures. Most masonry structures and foundations are destroyed. Well-built brick walls are cracked. Bridges are severely damaged or destroyed. Ground is severely cracked. There's considerable landslides from steep slopes and riverbanks. Sand and mud on beaches shift. Sand and mud on beaches is shifted. Water splashes over banks of canals, rivers, and lakes. Underground pipes break. There are open cracks and wavy patterns in concrete and asphalt. Railroad tracks bend slightly. Number 11, earthquake intensity number 11. A few structures remain standing. Bridges are destroyed. Broad fissures appear in the ground. Earth slumps and landslides in soft, wet ground. Sand and mud, charged water, ejected from the ground. Underground pipelines become completely out of service. Railroad tracks bend greatly. Intensity level number 12 of an earthquake. There is total damage to all works of construction. There are numerous rock slides and landslides. Riverbanks slump. Waves are seen on the ground. Objects are thrown up in the air. Did you feel it? The United States Geological Survey collects information from people who felt an earthquake. By completing questionnaires, humans provide information, much like seismometers, based on what they feel. The United States Geological Survey uses the data to create maps that show what people experienced and the extent of the damage. These are called Did You Feel It, or DYFI maps. Each map is created within minutes of each earthquake of magnitude 1.9 or greater. The maps are color-coded to show the distribution of felt intensity. The maps take advantage of the large numbers of internet users to gain a more complete description of events. Experiences can be contributed either immediately afterward or whenever it is possible. This creates a two-way street. Citizens can add valuable information on the extent of ground shaking and damage while learning about how other communities fared. Sometimes maps are made for smaller felt earthquakes or significant non-earthquake events, such as sonic booms or explosions. If significant numbers of reports are received. Shake maps are another kind of earthquake intensity map generated by the USGS. These maps are like Did You Feel It maps, except they are created using data from seismometers at set locations to estimate shaking intensity. The DYFI maps are a useful source of data in locations with few seismic stations. Shake maps provide near real-time maps of ground motion and shaking intensity following significant earthquakes. These maps are used by federal, state, and local organizations, both public and private, for post-earthquake response and recovery, public and scientific information, as well as for preparedness exercises and disaster planning. Did You Feel It 2015 map. Figure 1. The United States Geological Survey, USGS, map showing the distribution and intensity of all reported earthquakes felt in 2015. Different ground conditions, building construction, and other factors all play a role in how an earthquake is felt. As a result, the actual effect of an earthquake for a particular person or building may be significantly different from place to place. The USGS recommends that as many people as possible, including you, fill out a questionnaire. That's correct. Even if your community is already represented on the DYFI map for the earthquake, the more questionnaires that are received for your area, the more reliable will be the intensity assigned to that zip code. Even if you did not feel the earthquake, your response is important. In areas of lighter shaking, the not felt responses are needed to determine the percentage of felt responses as well as determine the boundary of felt and not felt areas. Okay, so you guys could contact the USGS on the internet if you feel anything, or if they put out a questionnaire in your area. Even if you don't feel anything, still record that and still submit that, because it will still help. It will still help map that, and in turn map the safety of the area. Earthquake effects. The main effect of earthquakes is shaking of the ground as seismic waves pass through the area. The main result of ground shaking is the collapse of buildings. Motion along a fault can break power lines, pipelines, roads, bridges, and other structures that cross the fault. The duration of an earthquake can affect the extent of damage. For example, buildings made of reinforced concrete may withstand a 20 seismic, that'd be a 20 on the seismic, 20 second, I'm sorry, they're talking about time. Okay, I need to get my values straight. Here we go. The duration of an earthquake can affect the extent of damage. So when they talk about duration, they're talking about time. So we're using seconds as a unit of time. Okay. For example, buildings made of reinforced concrete may withstand a 20-second main shock. However, they will collapse in a smaller magnitude earthquake that lasts longer. All right. Many earthquakes in the San Fernando Valley of California caused horizontal movement of the ground. In the past, structures had collapsed with this kind of motion. They were rebuilt to withstand this kind of motion. However, the motion of the 1994 Northridge earthquake was different. It had a strong vertical component. Many of the rebuilt structures and freeways collapsed again. Sometimes, some structures are affected by ground motion when others are not. All structures have a natural period of swaying. This back and forth movement is called an oscillation. The shaking of the ground during an earthquake may be close to the natural oscillation period of a building. When the oscillation of the ground is nearly the same as the natural oscillation period of the building, the swaying is greatly intensified. This is called resonance. The swaying of the building at its maximum contributes to the collapse of the building. You might know about resonance if you have ever been on a swing. The swing has a natural period of oscillation. When you pump your legs to go higher, you pump at about the same period as the natural period. Pumping at a different period would get you nowhere. The 1985 earthquake in Mexico City badly damaged or destroyed about 500 buildings. Ground vibrations were increased by the vibrational properties of tall buildings. This caused 10 to 14-story buildings to sway even more. It resulted in damage to many structures of this height. Nearby, shorter and taller buildings were not damaged. Building materials also make a difference. Stone, brick, wood, concrete, and adobe all have different responses to the forces they experience during an earthquake. Building design must take into account the structure of the building. However, It must also take into account the material from which the structure is made. In Figure 2, which is this image, in 2008, a magnitude 7.9 earthquake in China caused massive damage and killed at least 68,000 people. Okay, so you guys, as future engineers and builders and architects in a variety of different fields, you can use math and science to really solve some of these problems with structures and the structures being compatible with earthquakes. Okay, here we go. Fire is a secondary hazard in cities. Fire can cause much more damage than ground movement during an earthquake. In the 1906 San Francisco earthquake, 70% of the damage was due to fire. Fires start when ground motion breaks fuel lines, tanks, and power lines. Often, let me scroll down a little bit. Often, water lines are also disrupted or broken. This reduces the water available to fight the fires. One of the ways to reduce the risk of heavy fire damage is to place many valves in the water and fuel pipelines. If one part of the pipeline is damaged, those pipes can be isolated from the system. Landslides are another serious secondary effect of earthquakes. Earthquakes can trigger the failure of unstable slopes. The best way to minimize this hazard is not to build in areas with unstable slopes. Because buildings already exist in such areas, it is difficult to reduce the risk. The USGS National Seismic Hazard Map shows the probability that an earthquake hazard will occur in any given area in the United States. This map, as well as regional seismic hazard maps, forecasts the amount of shaking expected over a This map, okay, so they're referring to Figure 3 right here. Okay. This map, as well as regional seismic hazard maps, forecasts the amount of shaking expected over a specified period of time. The long-term probability that many parts of the central and eastern United States will experience earthquake hazards is moderate to high, even though these areas have not experienced large earthquakes recently. USGS seismic hazard maps, such as the one shown in Figure 3, are examined when designing buildings that can withstand ground shaking and are widely used by structural engineers and government agencies. Figure 3. The USGS National Seismic Hazard Map shows that earthquake hazards exist in many parts of the United States. All right, guys, check this out. So this is Wisconsin. We are literally right here where this blue starts. Beloit is right on the state line where it's south central Wisconsin, right on the center of the Illinois-Wisconsin border, but we're a little bit east of the center of the state line. So that puts us in this blue zone, whereas the rest of Wisconsin is in this white zone. So what does that mean? Well, here's the lowest earthquake hazard. Here's the highest earthquake hazard. So we still have low earthquake hazard, but we're not the lowest. We're a little bit above. So right here. Okay. So we have kind of a moderately low hazard. All right. Hazard, a low probability of earthquakes. Okay, here we go. Tsunami. When an undersea or nearshore earthquake occurs, a tsunami can be generated. A tsunami is sometimes called a seismic sea wave. Tsunamis are like the ripples that form when you throw a rock in a pond. Of course, they are much larger. Tsunamis occur when a large area of the ocean floor rises or falls suddenly in an earthquake. This causes waves to move away from the area. In the open ocean, the waves have very long wavelengths, greater than 500 kilometers. The heights of the waves are only a meter or so. The waves are so long and so low that ships at sea cannot tell they are passing by. If you have been to the seashore, you might have noticed that ordinary ocean waves get much higher and then break as they move into the shallower water. The same thing happens with tsunami waves, only more so. As they come on shore, the waves build to heights as great as 30 meters. Tsunami hazard zone. In case of earthquake, go to high ground or inland. Figure 4, this figure, it shows moving to a higher elevation is one way to protect yourself from a tsunami. One of the difficulties in preparing for tsunamis is their great speed. They move very fast over very long distances in the ocean. They can move at speeds of 1,000 kilometers per hour. On average, there are 2 destructive tsunamis in the Pacific Basin each year. An early warning system now monitors sea level around the Pacific. A tsunami can take several hours to travel across the Pacific. If a tsunami is detected, its estimated time of arrival is sent to areas in danger. People can then be evacuated from the area. This early warning system has had many successes. However, there have been some failures since it was begun in 1948. It works well for areas far from the earthquake. It is not very effective for areas close by because the waves move so rapidly. So basically what they're saying is if you're near an ocean and you feel an earthquake, that you should immediately head to higher ground. All right, guys, let me scroll down a little bit. The effect of local geologic conditions on intensity. Often, seismic waves increase in amplitude. Let me read that again. The effect of local geologic conditions on intensity. Okay. Often, seismic waves increase in amplitude when they pass from solid bedrock to softer material. For example, the amplitudes of the waves increase as they pass onto sand, mud, or landfill. The processes that cause this change are complex. However, you can get an idea of how this might happen. Think about what happens when you shake a soft, jelly-like material. Compare this to shaking a much more rigid material such as metal or rock. The Mexico City earthquake of 1985 showed how local geologic conditions influence the intensity of an earthquake. This earthquake caused about $4 billion in damage. It resulted in at least 8,000 deaths. The earthquake epicenter was about 300 kilometers from Mexico City. There were soft sand and clay deposits from an old lake bed under part of the city. This amplified or increased the ground motions 75 times. The amplification of shaking caused damage to some tall buildings. Nearby structures on bedrock were relatively undamaged. Liquefaction is another process that affects earthquake intensity. Hold on a second. It is a temporary change in water-saturated soil and sand. The soil and sand turns from a solid to a liquid state. It liquefies. The Marina District in San Francisco experienced this during the Loma Prieta earthquake in 1989. The district was built on wet landfill. Studies revealed that the landfill liquefied during the earthquake. The earthquake was centered 80 kilometers south of the city. Nearby parts of the city built on hard bedrock did not experience intensities as high as in the Marina District. So even though the Marina District was further away from the epicenter of the earthquake, it experienced higher intensity because of the soft landfill that it was built on. All right, guys, let me move down. So the type of ground that you build on matters. Okay, here we go. Earthquake magnitude. Earthquake magnitude is a measure of the amplitude of the seismic waves recorded on a seismogram. Charles F. Richter was a seismologist at the California Institute of Technology. He developed the first magnitude scale in the 1930s, called the Richter scale. His basic idea was to observe the maximum amplitude recorded on a seismogram at a known distance from an earthquake. Earthquakes could be ranked quantitatively by size or strength. The amplitude measured is the swing of the stylus. The wider the swing, the stronger the vibrations. The greater the vibration, the stronger the earthquake. The original Richter scale was developed only for shallow earthquakes. These were the ones measured in Southern California by a certain type of seismometer. Since then, the scale has been modified for more general use. Modern measurements of magnitude are still based on the amplitude of the waves. However, more sophisticated methods are used today. The magnitude of an earthquake depends on which method a seismologist is using. The results using different methods can vary by 1 unit or more. The United States Geological Survey describes earthquakes as minor magnitude. The United States Geological Survey describes earthquake as minor, which is a magnitude of 3 to 3.9, light, which is a magnitude of 4 to 4.9, moderate, which is a magnitude of 5 to 5.9, strong, which is a magnitude of 6 to 6.9, major, magnitude of 7 to 7.9, and great, which is a magnitude of 8 or higher. An important aspect of magnitude scales is that they are logarithmic. They are based on powers of 10. This means that seismic wave amplitudes increase by 10 times for each unit of the scale. For example, suppose an earthquake is a magnitude 6. The measured amplitude is 10 times that in a magnitude 5 earthquake. The largest earthquake in United States history was the 1964 Alaskan earthquake, which had a magnitude of 9.2.